Have you ever wondered how the web applications you use on a daily basis can find whatever you need quickly when you perform a searching task, like a shopping app or a movie streaming service? Index is one of the powerful tools that makes this possible. An index is like a book's table of content for your database. It creates a separate, organized lookup structure that points to where the data is actually stored, so the database can find rows quickly without scanning the entire table, instead of checking every single row to find what you need. The index lets the database jump directly to the right location. However, indexes are not created equal. B-tree indexes help with filtering, sorting, or ordering, but they struggle with natural language search. That's where full-text indexes shine. In this video, we will cover two major types of indexes that are widely used in relational databases that support scalable applications, including the B-tree index and a full-text index. Of course, there are other types of indexes as well, such as clustered index and hash index, but we won't cover them here. In combination, B-tree and full-text indexes cover about 85 to 90% of indexing tasks in typical application development. Many developers work their entire career using primarily B-tree indexes. Full index is common enough in modern apps that is worth knowing. As a result, we will focus our attention only on these two types of indexes. Let's start with the B-tree index. So a B-tree index organizes data in a sorted, tree-like structure with multiple levels. When you create a B-tree index for a column in a table of your database, the database builds this additional B-tree structure and stores it alongside your table data. So it's basically a copy of your indexed columns organized in a tree format, with pointers back to the actual table rows. When data is inserted, updated, or deleted, their corresponding operations will be slightly slower because you need to add data to this B-tree data structure or update or delete data from it. However, an advantage of a B-tree index is how fast it can speed up searching and sorting due to its balanced structure. Every path from top to bottom has the same length, guaranteeing that there would be a consistent and a fast lookup, typically finding any record in just 3 to 4 steps, even in a table with millions of rows. Let's look at an example of how to create a B-tree index and what that may look like. Think about a table named Movie from a database that supports a movie streaming web app. The table comes with 5 attributes, including movie ID, title, date, rating, and a photo. The rating column stores the average rating from all users. The developers of this app noticed that their users frequently sort movies by their ratings. Since this column is not a primary key, it doesn't come with an automatically generated index. Oh, by the way, when a column is designated as the primary key in a table, a B-tree index is typically automatically generated for that column in most database systems. It helps speed up potential searching and sorting tasks on the primary key. Since rating is not a primary key, it doesn't come with an automatically generated B-tree index. So to speed up searching or sorting on this column, you need to create an index yourself. To achieve that, all it takes is a simple SQL command. Create index, then it's gonna be followed by the index name, then on the target table, in the bracket that follows the table name, you will include the columns that you want to create an index on. So what does this SQL command do? It leads to the creation of a B-tree data structure using the data from the rating column alongside your table data. When searching or sorting is performed on the rating data from the movie table, the database system will be able to use this B-tree structure to speed up things. Similarly, if you are the database admin of this database and notice that sorting is performed frequently on the date column, it's natural for users to sort movies by release dates so that they can check out the latest movies. Since date is not a primary key either, so you need to create an index on it to speed up the corresponding sorting task. You can do it in the same manner as you create the index on the rating column. So far, you have seen two examples in which index is created on individual columns. What if it involves more than one column? Say the streaming app comes with a set of filters that allow users to filter or sort movies by more than one attributes, like both rating and the release date. If you notice the corresponding query is frequently triggered, then you need to create an index on the combination of the two columns, like this. All it takes is to put both of the two columns in the same bracket and separate them using a comma. Remember, you need the help from B-tree index when you need fast lookups, filtering, sorting on a non-primary key column. You typically don't take preemptive measures on indexing until you know enough about how users use your application. The empirical data is golden because it tells you where searching, filtering, or sorting actually happen frequently. Many developers work their entire career using only the B-tree index, because it is indeed the most important index. Standing alone, it probably accounts for 80 to 85% of indexing tasks in relational databases. B-tree index is great for many things that we mentioned, like fast lookups, filtering, sorting, or range queries on structured data, like numbers, dates, or exact matches. But it doesn't work well when you have to deal with a lot of texts. Imagine that you are building a blog and want users to search for articles containing the word database. With a regular B-tree index, you could only match exact values or use slow pattern matching like this query. This query uses a like clause that scans every row, which is painfully slow on large tables. Speeding up the search in a large amount of text data requires the help from a different type of index, the full text index. A full text index is specifically designed for searching within text content. It works by breaking down your text into individual words. We call them tokens. Then, removing common words like a and the. Then, creating a searchable catalog of where each meaningful word appears. Think of it like the index at the back of the textbook, but for every significant word in your content. What makes full-text indexes special is how it builds this data structure to support searching of text. Results of full-text index aren't just a match or no match. Full-text index can score results by how well they match your search terms, putting the most relevant results first. With the help of full-text search, you can search for phrases, handle plural forms, and even find similar words. For example, with the help from full-text index, searching running might also find run and runs. Last, full-text index makes searching much faster. Instead of scanning entire text columns, full-text index lets you instantly find all the rows containing specific words, even across millions of records. Now let's use an example to make further sense of when and how to use the full-text index and what that may lead to. Think about the movie table again, but this time it comes with a small modification, which is an extra column named description. This column stores the descriptive information of each movie, so it's all text of course, and each row would probably be very long for this target column. If the streaming app of this database supports users to search for movies by typing keywords or anything into a search bar, and primarily matches the input against the movie description, it is only natural that we speed up searching by creating a full-text index on the description column. The syntax of creating a full-text index varies a lot from one database system to another, so here, We will only quickly show you one example that works with Postgres, and focus on what structure is actually created instead. To add a full text index on the description column using Postgres, you need to add an extra column that conforms to a special data structure, and then create an index on that newly created column. So what exactly is generated when a full text index is created? Think about a movie table with 3 rows, and each row contains a description for the corresponding movie. When a full text index is created on this table, it will generate a structure that looks like this. As you can see, this structure stores the mapping from each word to the corresponding movie. You can think this as flipping the original data, or say inverting the original data, which makes searching extremely fast. You can directly look up each searching term and then get back the matching movies instantly, rather than scanning through every movie's description. You may also notice that some common words like and the are filtered out in this inverted index structure. So in a sense, we only kept the meaningful words. This structure is the reason why full text index can speed up searching tasks in texts. In this video, we covered 2 major types of indexing in relational databases, including B-tree index and full text index. If you find this video helpful, give it a thumb up, subscribe, and leave your questions in the comments. I would love to hear what's working for you and what needs to change. This video is based on the book Grokking Relational Database Design, which dives deeper into database design using real-world examples to explain concepts. You can find the link to the book in the first comment.